Hello and welcome everyone to the International Geomorphology Week 2023. This is the third time that the Executive Committee of the International Association of Geomorphologists is organizing regional webinars around the world. And 5 webinars have already taken place since this Monday. And like in the previous 2 years, the Northern Europe webinar is organized by Achim Alfred Beilich and myself, and we will chair this webinar today together. The Northern Europe webinar encompasses the 5 Nordic countries as well as the UK and Ireland. And we are very happy to have 6 exciting presentations from Iceland, Ireland, Finland, Norway, and Scotland today in this webinar. All invited speakers are in the early stage of their scientific career after completing their PhD. And we have a set of very interesting topics ranging from caves, glacier fluctuations, Greenlandic Vikings, Holocene jökulhlaups, permafrost mapping, and scratching beneath the surface.
Before I start, I would like to thank the committee for inviting me in this nice webinar and for giving me the opportunity to give this talk and talk once again about caves and what the caves can tell us about the landscape evolution. And for this presentation, I will use the Aspfjordgrotta, Aspfjord's cave, located in Arctic Norway. Before I start my presentation, I just want to say that this is a collaboratory work that started with a master of Magnus Torvik. His name is listed as on the authors list on the lower right part of your screen. And Magnus was supervised by Stein Erik, and then basically me and Randy, we jumped on this work, on this project, and now I will present you some of our initial results because we haven't yet managed to finish with this work, but I think it is quite interesting. So let me change this. Okay, why caves then? Why do we use caves to understand the landscape? Because caves are actually very good indicators about the past positions of the water table. And this is explained in Terek's four-state model. Caves can be formed above, below, and at the water table. And their geometry is indicative of in which position related to the water table they were formed initially. Of course, later on, the shape of the corridors is altered by changes in the water table. So if a cave, for example, was initially formed in a water table, at the water table, can be later on be found above the water table. And this will have a significant impact on the shape of the corridors and on the shape of the cave passages. And of course, on the sedimentation, on the sediments that we can see inside the cave. And this is explained really well in the work that Stein Erik and Joyce Lundberg done some years ago, many years ago. So in red here, I forgot to mention that in red are the references, and if anyone wants to read and learn more about the topic, can follow these references. And of course, finally, the cave, the speleothems, the cave deposits, the deposits that we can find inside the cave, are considered like ideal records for dating. And in this figure here, I'm showing you something from the work that Stein Erik and Ranveig have done some years ago, I think, 10 years ago, where they used some speleothems, two certain different type of speleothems, so they can understand the glacier advantage, to date the glacial cycles. Again, here is the paper. You can read more if you like. So what are these speleothems that are so important? First of all are these chemical deposits, the flowstones and the stalagmites that are actually indicative of a phase that the cave is drained. It is under subaerial conditions, so these deposits can be formed inside the cave, and we can date them. And later are these concretions that you can see, as you can see here in magnification here in this figure, that they are actually showing us periods where the cave was filled with sediments and the water was moving inside the sediment. It was super saturated. It was moving inside this classic sediment, and these deposits, they were these concretions, they were formed, and now they are left here as evidence of this past processes that I've just described to you. So why Aspfjordgrotta? Because Aspfjordgrotta is a cave that is found in northern Norway. It is only 150 kilometers east of the southernmost islands of the Lofoten archipelago, it is close to the coastal mountains of Salten area. That these mountains, they present this very typical alpine glacial topography with pointy hills and etc. And of course, it is very close to the sea coast. The Aspfjordgrotta is here, and you can see the coast of Norway is here. So what are the methods that we use? And this is like I will show you now the methods that we usually use in the study in order to study caves. But I will use an example, of course, the data from Aspfjordgrotta. So what we do first, what is the first thing that we do when we enter the cave is to survey the cave. And in order to survey the cave, we are using a certain methodology and a certain equipment. This equipment is actually a modified rates finder that with a push of a button, we can record the distance, the inclination, and the azimuth of the shot. So having this in mind, we are making our survey line like this, as you can see here. And then in every station, we are making, of course, stations. And in every station, we are taking like this vertical to the main growth of the passage shots in order to describe the shape of the passage better. Then, using some cave-specific software, we can import these, we can extract these shots and these measurements that we've made in the cave as points, and we can import them as a point cloud in GIS software. And from there on, we can make all this analysis using this data set, like make accurate cross sections, etc. Of course, we map the sediments that we found and the other speleoforms, landforms that we found inside the cave, because they can help us understand the hydrological regime that enable the sediment deposition. And here I'm showing some pictures from inside Aspfjordgrotta, where here you can see some cemented sediments. Here you can see some cobbles and boulders in this corridor. And here you can see very fine material, fine sediment that is stuck on the ceiling of the cave. And of course, finally, in order to set the time frame under which these changes or these different phases in cave evolution took place, we collect speleothems, as I mentioned before, that are suitable for uranium series dating. And this is what we have also done in Aspfjordgrotta. We collected quite a lot of speleothems. So what are we getting afterwards? What are the results that we are getting and how we are using them? Using this survey methodology that I showed you, we can get a very accurate 3D model of the cave. I forgot to mention that we are using a fixed point on which we are anchoring the whole survey. So this fixed point is usually the entrance of the cave, because we can get the coordinates using a handheld GPS or using the map. So from that point, since the whole survey is anchored on that point, the whole survey is georeferenced. And for example, here you can see that the Aspfjordgrotta, this cave, it is formed in a 100 meter elevation span. So the highest point of the Aspfjordgrotta is found here. It is around 325 meters, and the lowest point is the exit here, and is in 225 meters. Of course, we are not only using the 3D model of the cave, we are also making these plan view maps, like this one here. This map is, this plan view is, it is done inside the cave. So this is why it looks like this. So we have the plan view of the cave inside the cave as we are taking the measurements, and then we can use it in order to map the cave sediments and make these nice thematic maps like this one that you can see here, where we depict where we can show the sediment deposition, the various sediment deposition along the cave. And of course, we can also use it as a base to map different things. About the datings, unfortunately, this is why we are stalling with this work. From Aspfjordgrotta, I don't have any datings to show you, although we've collected a lot of samples and we tried to date them. We faced some problems with the lab, and now we are forced to send them to another lab. So we are still waiting to get the results from the certain cave. And now let's move on the discussion. I'm trying to be very fast, so forgive me for this. So for Aspfjordgrotta, for example, when based on the shape of the corridor and the sediments that we were able to map there, we were able to say that this part, the upper part, let's say, of the cave, has experienced 4 or 5 different evolutionary stages. The first one, of course, the initial one, which is the stage where all these proto-karstic conduits are formed and then they are expanded. We can distinguish this in this stage in 2 different phases, let's say. Then we were able to decode and find that there was another stage where this corridor was filled with coarser clastic material, like here. In the following stage, we were able to see that there was some fine grained clastic sediment deposited here in this corridor. And of course, the final stage, which is the stage that represents the present day setting in the cave, and where the passage has this form, and these are the sediments we can see. And with the blue here, the flowstone that we collected and we try to date is depicted. So we were able for this part to understand that there were 4 or 5 stages, and for the lower part, for the middle part, actually, for the middle part of the cave, we were able to understand and to decode 6 or 7 different evolutionary stages. So again, we were able to we can say that there was an initial stage where the protoconduit was formed, and then this protoconduit was expanded. The initial, let's say, cave geometry took place, and it was settled. Then in a later stage, the cave experienced some base level drop, and then was this there was a lot of erosion on the first phreatic conduits, and these conduits, they got this very characteristic keyhole-like shape. Following these passages, they were filled with sediments, clastic sediment, that was again removed. The passage was then acquired let's say, a morphology that is more similar to the present day morphology. The shape of the passage looks somewhere here is established, and it looks more like what we can see today. Then again, the corridor is filled, the passage is filled with sediments. Again, the blue color for the sediments are the old ones that they are actually cemented, and they were left there as traces of these past states. And then again, the final states, the states that we can see today, where the passage is empty of sediments, the sediments were flushed away, the passage is empty, and only these few traces are left in some points. And based on this, we were able to make a story that is not that we cannot tie it entirely with certain datings, but the story goes like this. So we have a glacier, under glacial states, the under glacial setting, the protoconduit is formed, and we believe that this might have taken place sometime between MIS6 and MIS10. Then, of course, again, under the glacial conditions, the cave is expanded because there is a lot of water flowing inside the cave. And the protoconduit is starting to expand. The cave is full with water at this stage. And then we have the third stage. We can actually distinguish these states in A and B phases, where we have a base level drop. And this is happening probably during deglaciation, because now the cave is starting to experience Vadose conditions. So part of the cave might be outside of the, above the water table. And we have a lot of aggressive water running through the cave, which is actually the melt water. And then during interglacial conditions, we believe that we have the flowstone formation. Again, the datings will confirm this or not. And as you can see here in this picture, we can see the initial conduit, the phreatic conduit, and of course the Vadose entrancement of this initial conduit. Then we have a fifth phase. Of course, there is a fourth phase that we cannot detect inside the cave, but in this fifth phase is again a phase that is under deglaciation, where we have again great amounts of water that are flushing away the sediments from the cave. Some of these sediments are left here cemented, that later, of course, they were left there and they were later cemented. And we believe that in this stage, there is quite a lot of abrasion, and the flowstone is partially eroded, the flowstone that I showed before. Then we have the sixth phase, which is a phase which is under, again, glacial condition, and the cave is flooded with water. And then we have this seventh phase that, again, we can distinguish in A and B subphases, where is a phase that is actually the cave experiencing during deglaciation, where the cave is drained from the water. So there is no water left, or only Vadose water that is flowing very at the lower part of the cave. So since the whole cave is drained, the cave is experiencing a lot of collapses. Blocks are falling here because due to lack of buoyancy, there is no water to support these blocks, and these blocks are collapsing, are falling off, as you can see here in this picture. And then there is this other phase, the 7B phase, where sediment is filling the lower part of the cave, which is followed again by abrasion. and might be this abrasion, this erosion that we can see in this in the flowstone. We don't know yet. The datings will confirm this theory. And of course, we have the deposition of the finer material and the concretions that I have showed before. And the E8 phase is the current day phase. So thank you. That was all for me.
Well, thank you so much again for inviting me to participate today. I'm really excited to share with you all some of the results in progress, I should say, from an ongoing project I have in collaboration with researchers also here in Ireland at the University of Galway, as well as at the University of Maine in the United States and Victoria University of Wellington in New Zealand, really kind of using what are, I would argue, the really spectacularly well-preserved landscapes and glacial landscapes in particular we have here in Ireland to address questions regarding past climate change, the causes of past climate change and the sources of natural variability in our climate system. And in particular today, I'm going to be sharing some of our work at this field location in particular, which is the Glenaby Mall, which is on the western slopes of Lugnaquilla, the mountain you see here. But before I get into too much detail with our field site and really introduce you to the place, I want to kind of get at the motivating questions, like what we're trying to investigate, what questions we're trying to answer with this project. And to start, this is a graph. Many of you have probably seen some version of this in the past. This is reconstructed temperatures, surface temperatures from Greenland, taken from the NGRIP ice core. So here, temperature in degrees Celsius is on the y-axis, time in thousands of years ago is on the x-axis. Temperatures are plotted here in blue, and modern temperatures are marked just by the pink star at the far right-hand side of this graph, the far right-hand side of the image, with future projected temperature change in black just beyond that. And you can see how rapid ongoing modern changes and projected immediate future changes in our global temperature are, particularly compared with this in the general record of this plot. But this graph in particular was published by Janssen et al. In 2020 as part of their exploration into using past climate change as a way to inform our knowledge and understanding of future climate change. And in particular, they highlight in red in this plot instances or periods of time in this ice core record when there's evidence of very, very rapid shifts in climate, rapid warming in particular, that they argued might be important for us to use as cognates in climate models. If we could accurately project or accurately reconstruct these time periods, these rapid changes in climate models, we could more accurately model future change. But traditionally, models have a very, very difficult time reconstructing these abrupt changes, these abrupt events. And there are, we think, a number of reasons why this could be the case, including seasonality bias in some of these paleoclimate records, but also the fact that within the North Atlantic region, where we see many of these abrupt changes in ice cores or ocean sediment records, there are very few terrestrial records of climate change that go back through this period and cover, in particular, the last 20,000 years when there have been at least 2 or 3 instances of these rapid changes that actually bookend or border periods of extreme cold, including the Heinrich Stadial 1 and the Younger Dryas. These periods when we predict glaciers would have been more extensive, but understanding how these climate changes have been felt or experienced in the terrestrial realm really is a region where we're hoping to build out our knowledge base and data set. And so that's what we're really doing with this project and trying to take advantage of not only the very well-preserved landscape in Ireland generally that shows evidence of past glaciation, but this site in particular was really exciting because we think, held a particularly well-preserved record that would span back over the last 2 cold intervals through Heinrich Stadial 1 through the Younger Dryas in particular. So in this map and throughout this talk, actually, I've just marked the peak of Lugnaquilla, the top of that mountain, with that yellow star, so you can kind of follow its location throughout. Now, this image I took from the western slopes, the western foothills of the mountain looking towards the east. Next, I'm going to show you an oblique satellite image of this peak, but from the same vantage. So this is that oblique satellite view of Lugnaquilla. The peak of the mountain is again marked with that yellow star, and north is to the left-hand side of this image, just to help you orient yourself. The North Prison Valley extends from the peak of Lugnaquilla towards the west out onto the plain of the Glenavy Mall, and immediately to the north is the Leo Valley. And if any of you are familiar with glacial geomorphology, glacial landscapes, your eyes are probably already noticing a number of discrete, very clear, dramatic glacial landforms here held within these valleys and on the Glenavy Mall. And it's these landforms we wanted to target, because during the last glaciation, during the last glacial maximum, ice filled both of these valleys, and at its maximum, these glaciers came together, coalesced to form one large body of ice that extended out onto the glacier, into the Glenavy Mall. And when later on, climate warmed, climate changed, the ice melted, it left behind these discrete ridges and mounds of sediment called moraines that I've highlighted here in pink. And these are fantastic because if we know the size and extent of a glacier, we know that its size and extent is tied directly to prevailing climate conditions. And so if we can map the extent of the glacier, we know we can work out through glacial modeling what the climate had to be or what the potential climate situation was. In addition, if we can date these deposits, then we know when these conditions prevailed and when changes happened. And so that's really the crux here. We want to map, date, and model these glaciers. Now, here, there's been no previous work done to date these glacial sediments at the Glenavy Mall or on Lugnaquilla, where you see them here. But it's been long assumed that these most distal moraine ridges, these most distal sediments that represent the most expanded ice position, would correspond with that cold Heinrich Stadial 1 period between 18 and 15,000 years ago, and that the small Corey moraine immediately below Lugnaquilla's peak would correspond with that Younger Dryas period, roughly 12,000 years ago. And so our hope is that this site would give us insight into not only these cold periods, but to the abrupt transitions that border them. So really, ultimately, that's what we wanted to get at here. What can the glacial record, the glacial landscape here tell us about the terrestrial expression of past climate change? And to do this, to date these sediments in particular, we use a technique called beryllium-10 surface exposure dating, which, if you're not familiar, has really revolutionized geomorphology in the last few decades. It's fantastic. But in the case of a glacial landscape where we're dating glacial landforms, you can imagine that a simple mountain glacier system like this one I'm showing here in cross-section is made up of a zone of accumulation near the glacier's top where it's gaining mass, a zone of ablation near its toe where the glacier is losing mass, and where these two processes are equal, where the glacier gains just as much mass as it loses over a given year, we have the idealized equilibrium line altitude, equilibrium line elevation. When climate is stable and steady, the glacier is in equilibrium with its climate, the geometry and extent of the glacier will remain much the same. And the glacier will deposit sediments along its margin that mark its extent at that point in time. If, however, climate changes, if it becomes more dry or it becomes more warm, the accumulation zone will actually shrink, will become smaller. That equilibrium line will have to rise or will rise. And so the glacier as a whole will become smaller to reach a new equilibrium size, equilibrium geometry with its new prevailing climate. And when the glacier retreats, it will abandon those sediments it had deposited at its margin, those moraine sediments that are now left behind. And when the ice is gone, these sediments are now exposed to incoming cosmic rays, high energy particles from deep space. And these particles, on occasion, will actually strike particular atoms or molecules in these rock surfaces, in these boulder surfaces. And in particular, when these high energy particles strike single atoms of oxygen-16 in a single molecule of the mineral quartz, they can kick out a few protons and a few neutrons, and what was once a single atom of oxygen-16 will become an atom of beryllium-10. So we can come along, collect a piece of the surface of these rocks that were left behind by the glacier, and if we very precisely measure the concentration of beryllium-10, then we know how long ago the ice abandoned the rocks on the landscape. So that's how we can get at the time, the age of these landforms, to add chronology to these data sets. Now, the Glenavy Mall I mentioned is spectacularly well preserved. And the major reason it's so well preserved, this landscape, is because there's been no development of the land. It's an active military firing range. It's an artillery range, a training ground. And so we were very lucky to gain permission to access these lands, to explore, to take samples. But at all times, we had to take great care. And we actually had a military escort with us on each one of our visits, because there is a good amount of exploded and unexploded ordnance. Here in this image at the bottom, you can see exploded ordnance. So this was no longer a danger as we walked through this area, but it was something we had to be aware of. And it did mean that we could not always explore every area we hoped to, access every landform we hoped to. Originally, we'd hoped to collect some sediment cores from this region. And the Army said absolutely not, but they still were able to give us really fantastic access. These are just some photos of sample locations, sampled boulders that were deposited by glaciers in the past. The image on the left is from a boulder on the crest of that Corey moraine I showed you, thought to associate with the Younger Dryas. On the right is an image of me sampling a boulder on that outermost, most extensive moraine ridge, so the most extensive ice extent. So going back to that same satellite image now, though, I'm going to share with you our chronology, the results we have in hand thus far for this project. So starting with this image, I'll draw in those major moraine forms, those major sediment ridges that show former ice extent here. These now are the individual ages we've acquired thus far from these landforms. So just to walk you through this image, each yellow circle is one single sample location, and the associated beryllium-10 surface exposure age is in black. Any outliers are colored in red, and the arithmetic mean landform age, so the average age of any given single moraine ridge, is shown in larger font in blue. And so that outermost ice position, that most extensive ice position that we have mapped and dated here, dates to 22.8 thousand years ago, so roughly 23,000 years ago. That means that 23,000 years ago, ice was most extensive in these valleys, after which point the climate changed, ice began to pull back and began retreat. By 21.3 thousand years ago, the ice coming from both of these two valleys had separated. And in the North Prison Valley, towards the south, on the south side here, ice had actually retreated by at least 1.5 kilometers up valley from that earlier 23,000-year-old position. And finally, that uppermost Corey moraine, we have a number of samples that provide an arithmetic mean age of roughly 18,000 years. So immediately, our assumptions got turned on their heads. These three landforms and all these ages really are much older than we were originally expecting. These all essentially predate Heinrich Stadial 1, and nothing correlates with the Younger Dryas. If we go back to that earlier image I shared with you, if we were expecting these landforms to fall within that Heinrich Stadial 1 Younger Dryas time period I have marked in green, these three pink bars instead show the approximate ages of those three landforms. So what are the implications of this? What does this mean? Well, first, we can compare these results with recent publications showing ice sheet extent at this time, or inferred ice sheet extent and recession during this time. The Brit Ice project, some of you may be familiar with, just last year published a fantastic summary of their work to date, where they've done just an immense job of bringing together so many different offshore records and onshore records of past ice sheet extent to really summarize what we know about ice sheet position and ice sheet recession following the last ice age in the North Atlantic region. Here, again, Lugnaquilla is marked with a yellow star. The left-hand side is showing the ice sheet reconstruction at 23,000 years ago, and on the right-hand side at 22,000 years ago. And so this would suggest that here our results would probably favor a more minimum ice extent as drawn in by the Brit Ice team, rather than their current optimum or certainly ice maximum. Because if we have evidence of mountain glaciation at the Glen of Imal, if there's a mountain glacier, we know we can't have an ice sheet overhead. That's just impossible. And so this places a bit more limitation on exactly where the ice sheet limit had to be at this time 23,000 years ago. Beyond that, I mentioned earlier, we're also modeling these glaciers because originally we wanted to see what the inferred temperature change might be, what the temperature and climate conditions might be. So this is work of Sean Eaves at Victoria University of Wellington in New Zealand. And so this is a glacial model overlaid atop a DEM. The north is towards the top of this image, and Lugnaquilla is marked by that yellow star. And here, Sean Eaves has used a simple mass balance glacial model to grow ice to the position of that 22.8 thousand-year-old moraine. So here everything is colored in by ice thickness, but he just grew ice out to this extent and then inspected what the associated climate conditions required for this would be. And so with modern precipitation levels, so precipitation just as you would experience today, to grow ice to this position would require roughly 9.2 degrees Celsius of cooling on the mean annual relative to today. If, as we think was likely the case, conditions were a bit more dry during the last glacial maximum, with a 20% reduction of modern precipitation, we would require roughly another half degree of cooling on top of that, so 9.7 degrees colder than modern. And with 40% reduction in precipitation, 10.3 degrees Celsius of mean annual cooling. And so this is still kind of ongoing work. We're modeling each of these ice positions to see the magnitude of change, the potential bounds on different aspects of climate, such as precipitation and seasonality. But this is just to give you an idea. And this is actually a little bit less cooling than has been suggested by similar studies that have taken place in Wales. So looking at the Welsh ice cap across the Irish Sea. But within still those general bounds of 10 to 12 degrees of cooling. So I'll say, as of a week ago, that was where I was going to end my presentation. But we just got some brand new data a few days ago from the site that I thought would be really exciting and fun to share. So these now are still those same data I showed you before, all collected from within this valley and on this plain coming from the mountain glaciers. While we were at the site, we also collected samples from boulders not within the valley, but high on the ridgeline above the valley that would represent not a single moraine ridge, but boulders set down on the landscape as the former ice sheet that covered this area thinned or retreated past. And so here are these two ages that we required there. One, you'll see, dates to roughly 35,000, the other roughly 40,000 years before present. So much, much older than we were anticipating. And I'll show you just one photo from the field so you can see what these look like in action. This is one of those perched boulders set down on this slope. This sample is the one that returned the age of 34.6 thousand years ago. You can see it's actually been set down on another boulder. And really the only way that these boulders could be here is being carried by ice, likely by the former ice sheet. There's evidence of glacial modification, glacial erosion on these rock surfaces. And in the far background, you can just see coming out of the mist that 18,000-year-old moraine, just to get a sense of the position here. So because we only have these two ages, we don't necessarily want to make any firm suggestions or interpretations with these data just yet, but there are a few possibilities. If these really do reflect the last time the ice or ice sheet moved past or retreated past these highlands, it would suggest that the ice sheet itself is likely much less extensive during the last ice age than might be inferred from interpretations like those of the Brit Ice Project. I'm not ready to go there quite yet, but we have a number of samples in addition to these that we've now sent on for measurement. So we hope to get a little bit more information there. Other possibilities, though, are that these have a very complex exposure history. If the ice sheet here was perhaps a little bit thinner than anticipated, it could have been cold-based and non-erosive. And so these rocks could reflect multiple periods of exposure and glaciation, not simple last duration of exposure. There's also the possibility that because maybe they didn't come from very far away, they weren't well eroded, and that beryllium has been building up over, again, many time intervals, not just the last duration of exposure. And so with those additional samples we sent for measurement, we hope to learn a little bit more about these samples and what they represent. But for now, it's kind of TBD. But just to wrap up, our evidence shows that mountain glaciation at this site culminated roughly 23,000 years ago, followed by retreat, and which is roughly indicative of, we think, 9 to 10 degrees Celsius of cooling relative to modern. And this site actually could have potentially been ice-free early on during Heinrich Stadial 1. So with that, I don't want to go too far over time, but thank you so much again for inviting me here today, and I'm happy to take any questions.
Thank you so much for inviting me here today. And I'm going to be talking to you about what can glacial geomorphology tell us about the Greenlandic Vikings during the Little Ice Age. And the Little Ice Age was essentially a period of renewed climatic cooling where ice fields and the ice sheet actually started to re-advance. I did this work as my postdoc at the University of Aberdeen, and it's very much, as you see as we go along, it's very much a interdisciplinary project. So I'm just flagging up my co-authors there as well. So overview, I'm going to talk about the importance of tidewater glaciers and why we need long-term records of tidewater glacier change, specifically focusing on Kangiata Nunata Sirmia, which I'll shorten to KNS for obvious reasons, the glacial geomorphology, and demonstrate how our project reconstructed KNS's advance over the last millennium. So this includes the medieval warm period and the Little Ice Age. And what can all of this tell us about the Greenlandic Vikings? So I'll kind of dot that about this talk. So a bit about the Greenland ice sheet. It's 3 kilometers at its thickest, and surrounding the Greenland ice sheet, so draining it, are a number of land terminating outlets as well as tidewater. So tidewater is anything that terminates in marine or fjord conditions. Around the periphery of Greenland are a number of glaciers and ice caps which amount to about 100,000 square kilometers. And if we were in a Hollywood film and the whole of the Greenland ice sheet melted overnight, it has the potential to raise eustatic sea levels by about 7 meters. So obviously that's not going to happen, but the point is that much of the work that we do on the Greenland ice sheet and the ice caps is trying to feed into understanding what is the contribution, past, present and future, to sea level changes. So we actually don't know that much about tidewater glaciers. So we've got data from what's known as the observational record, so the satellite era. So that spans the last sort of 30 to 40 years. But prior to that, we don't really know what happens with these systems. So this is an example of Jakobshavn Isbrae, which is probably the most famous tidewater glacier in Greenland. It flows pretty fast with a contemporary calving flux of 35 cubic kilometers a year. And you can see from this figure that there's been substantial and consistent retreat since its Little Ice Age maximum. And this is kind of a pattern that we're seeing throughout Greenland, that in recent decades, these tidewater glaciers have undergone substantial retreat, thinning, and an increase in velocity. And especially with some of these tidewater glaciers, they're now starting to reach an area of topography where they're not so confined, so they have less shear stress pinning them to the sides. So we're starting to wonder whether we're going to get this sort of positive feedback where they sort of have this runaway effect in terms of retreat. And in terms of draining the ice sheet from mass loss, they can be substantial indicators. So Jakobshavn drains 6.5% of the Greenland ice sheet, which is actually a huge amount. So carving, this is Jakobshavn itself, and you can see all of the icebergs in front of Jakobshavn. So that's carving, so it's the iceberg production. And carving accounts for about 50% of the mass loss from Greenland. And this coincides with a warmer climate. And so what we want to know is, will this increase in the future? And there's a need to model this link. So anything that's future is obviously prognostic modeling. And we need to model that link between carving and climate. So I'm no modeler by any stretch of the imagination, but the carving community was saying to us that, you know, we understand, you know, basically what these systems are doing in a warming environment. We know they're retreating. What we don't know is what happens to them during a period of cooling as well as warming. And we don't know what happens to them on a much longer time frame beyond the satellite era. So that's really where this project came in. And our aim was to reconstruct the longest ever record of Greenlandic tidewater glacier behaviour. So we focused on KNS, which is about 5 kilometres across. And you can see here the Little Ice Age maximum. So that's denoted by the geomorphology. So discontinuously throughout Greenland, you have this trim line. So that's where you've got a vegetated surface versus a glacial scoured surface. So we can have a pretty good handle on the former sort of dimensions of these outlets, if you like. And something to note here is that, I hope you can see my arrow, is the present day fjord is absolutely ice choked with carving. So it's actually very difficult to get access to some of these outlets. So we wanted to reconstruct the advance over the last 1,000 years, which is actually quite tricky when it comes to looking at glaciers, because as they re-advance, they tend to destroy or rework pre-existing material. So that's actually quite tricky in itself. And as with any sort of paleo reconstruction, the more proxies you can use, that's just my opinion though, the more proxies you use, the more robust your reconstruction can be. So we used a number of proxies, and I'm just going to be touching upon the geomorphology, the archaeology, and the chronology. And this was our field team. We also had a marine team, which were diving, but this is the terrestrial team. We spent 2 field seasons out in Greenland collecting samples, and importantly, we got to ground truth the mapping, which is kind of unusual at sort of ice sheet scale because you don't have the time to do all of that. It's quite vast distances, and most things tend to be done through remote mapping. So that was quite important about this study. So why did we pick KNS for studying millennial scale change? Well, it's the most dynamic tidewater glacier south of Jakobshavn. It's also relatively close to Nuuk, so the access to this glacier is a little bit easier than some of the other outlets across Greenland. It's surrounded by a number of other tidewater and land terminating glaciers. Importantly, it has really well preserved glacial geomorphology, which helps us to constrain the past geometry of this outlet. We also have a number of photographic and written expedition records, which again help us to locate where the terminus was at a particular point in time. And there's also a number of Norse settlements dotted throughout this region, and we were really interested in those that were closest to the ice sheet, and how did the Norse possibly react when the conditions started to deteriorate. So The glacial geomorphology, the first port of call was to really do a map of the entire area. I always go in with kind of no preconceptions, because if you look at other people's mapping, it can kind of skew your interpretation. I use a range of different data sets, so Landsat, DEMS, orthos, and as I said, importantly, we got to ground truth a lot of this. I followed a morphostratigraphic approach, which is essentially, if you take this black line, which is from the geomorph, this is the Little Ice Age maximum, and you can see it's very much constrained by the topography. So you're going to get a certain land system associated with that. Whereas if you're looking at pre-Little Ice Age and Holocene fluctuations to the west here, you're going to get a different landform signature because it's overriding the topography. So this is, I think this was Aster imagery actually, and which is quite old. And obviously the older the imagery, it tends to be more pixelated and things like that. But I found that the Aster imagery was actually really good at picking out large scale erosional and depositional features, which you can see here. So I've just changed the angle of illumination in these. It's the same image and the same data set, but you can really clearly see some of these landforms here. Then you can use, say, ortho photos, and I appreciate you might not be able to pick out the detail on your screen, but that's where you can start to really map the finer detail of what's going on. So this is the final map, which was published a while ago, but if you're interested, that's in Journal of Maps. So for the purpose of this talk, I'm just going to focus on two sites, which is V15 and V53D, and that's where there are Norse settlements that are closest to the ice sheet. So constraining the advance of KNS, we use the geomorphology. This is the trim line, which denotes the Little Ice Age maximum. And that shows where KNS was at the maximum. What you have here is Iceland, which is a lake. And at some point, as KNS started to advance towards its Little Ice Age maximum, it started to drain westwards into a really large valley called Osmanadalen. And the geomorph is telling us, that there's no way that KNS advanced into Osmanadalen during the Little Ice Age. So this was essentially deglaciated. So what you would have had is a pre-vegetated surface, which you can see in parts of that photo. And then when meltwater started to route into this valley, you would have had to have a change in sediments. You would have got that influx of glacial rock flour and silts and sands. So it stands to reason, if we could find that pre-vegetated surface and date it, it would give us the first sort of handle or actual chronological control on when KNS was at that configuration. So when it had reached a certain thickness and extent. So we know that we can use this because since 2004, from the satellite data, KNS has thinned quite substantially. And so it's switched off the drainage. There's no more meltwater going into Osmanadalen, and it now drains into Kangersunek Fjord, and it's stayed that way since 2004. So there's no change in sort of sedimentation. So what did we find in Osmanadalen? You can see here in this bottom left photo, that's where the meltwater would have routed over into the valley. And the top picture here, you can see the dry riverbed, and you can just about see our tents in this. It's a really large valley. And so what we did is there had been no previous work in this valley except on the Norse settlements. So we dug a series of pits across the valley, and they all broadly showed the same stratigraphic sequence, which was this sort of dark peat layer overlain by the glacial sediments, and then you've got the top vegetated layer. So I used sphagnum to radiocarbon date a series of these layers. And this bottom layer is the one that we're really interested in. And what this does is it gives us a date for when KNS was at that configuration and when the water started tapping into Osmanadalen. So that gives us our first chronological tie point, if you like. So what happened with the Norse? So this is a huge valley. It's about, I think it's about 25 kilometers long. It's absolutely massive. When we radiocarbon dated other layers, it showed conventional settlement and abandonment dates. What was interesting was that there was no pollen evidence to really show that they were growing crops in their home field sites. They have what's known as a home field. There was a little bit, but not very much at all. So what we think was actually happening is at the mouth of this valley, there's a buried church, there's a number of other settlements, and we think it would have been quite accessible at the time. And so it's possible that this was more a trading location. So this is a storehouse in the top right-hand corner, and we think it would have been trading for the meats and the skins and things like that. So they weren't actually growing crops in this area. But what it does show is that despite the amount of meltwater that would have been coming into this valley and the conditions deteriorating at the time, the Norse did not abandon the site early. So they didn't seem to be bothered by the changing climatic conditions. So following our first high point at Osmanadalen, KNS started to advance down valley to its Little Ice Age maximum. Now what we have here is a land terminating outlet, Kamanasa Upsermia. And so it would have just drained meltwater into Kangasunak Fjord. But as KNS advanced down valley, it would have dammed this particular location. And so you would have started to have an ice dam lake form in this part. And so again, we hypothesized that we would think there would be a pre-vegetated surface. And as soon as it dammed, you'd start to get glacial lacustrine sediments forming. So if we date that organic layer, we'd get another chronological tie point of when KNS got to that particular location. So we know this from the geomorphology. So this is going back to that really clear double moraine system that we can see. And also the only photo that we had, because no one's been to this area, it was this photo from 2012, and the sort of light sediments we hypothesized were that sort of lake sediments. So what did we find? We found that peat layer. It was discontinuous throughout the whole site. Above it was the glacial lacustrine sediments, and below were the marine sediments. And when we dated that peat layer, we used bark actually, which is like the gold standard of material for radiocarbon dating for here. It came out at 1236 CE. So it means that KNS had got to that point. I hope you can see my arrow here. Had got to this damming point by 1236. So what does this mean? So following the change in meltwater routing at Osmanadalen, KNS advanced down valley at about 113 meters per year, which is really quite rapid. And it's almost analogous to rates of retreat that we're currently seeing. So that's showing that the Tidewater Glacier is really sensitive, not just to warming, but it can be very sensitive to climatic cooling as well. And so it started to advance during the medieval warm period, and contrary to its name, there was actually a cooling in Western Greenland, and we know that from the Alkanone summer temperatures. It also coincides with a number of other re-advances at that time in Baffin Island and Arctic Canada. So it got to this point at 1236 where it dammed, and what happened is that it didn't get to its Little Ice Age maximum until 1761. So we actually think for that sort of 500-year period, the terminus was just advancing, retreating, but we don't think it ever retreated behind this 1236 marker, if you like, because there's no stratigraphic evidence in the sediments to show that that lake ever drained and then started to refill again. So we think that the terminus just waxed and waned slightly. Now, the geomorphology is showing us here that this is the trim line associated with KNS, and you can quite clearly see it there. This is also the trim line on the other side of the valley. And you can see here that it's very close to V15, which is the Norse settlement. So we wanted to know, as this glacier was coming down the fjord, how did the Norse react to this? Because it would have been moving quite quickly. So when we dated the sediments from V15, it showed a conventional again, a conventional settlement and abandonment date. So they didn't leave this site early because KNS was advancing down valley, which is something we didn't really expect. So it got us thinking, okay, well, this is the current conditions in the fjord. So this bottom left-hand photo, you can see that it's completely choked up with ice, and it actually took quite a while to get the right conditions to travel across the fjord to V15 because of the amount of iceberg production. So it got us thinking, so they couldn't have had this much amount of icebergs during that time because it's just impossible for them to get access in and out of this site. So what we actually think the fjord looked like was this. So we think there was a lot less iceberg production, and that's because in order for KNS to have this sort of slight advance retreat, it wouldn't have had a lot of mass loss from its system. So there wouldn't have been much iceberg production. And so the actual fjord itself would have been quite ice-free, allowing them access in and out. So that's why the Norse weren't too bothered about KNS being in close proximity. So what are the implications of this? It shows we've demonstrated that there's a rapid and sustained tidewater glacier advance during the era of Norse settlement in Greenland, and that regional cooling can drive glacier advance rates analogous to ongoing retreat rates across Greenland. So they're very sensitive to cooling as well as warming. The less extensive forward melange, which is like all the icebergs in the fjord, and lower calving rates during advance are inferred from the presence of V15, which are presently inaccessible by boat. And it supports the counterintuitive notion that the deteriorating climate may have actually aided the Norse by allowing them access to the inner fjord system. This in particular illuminates actually how resilient the Norse are in Greenland to dramatic environmental change. And we've provided insight into the dynamics of tidewater glaciers, both during the advance and the retreat phase. And importantly, modelers can now use this data to validate models against a range of conditions to improve prognostic simulations. So these were the final figures for the paper, and it came out last year, and we made the front cover of Geology. So this is the only famous thing I'm ever going to do, so I thought I'd advertise it here. But thank you very much again for inviting me, and I'm happy to take any questions.
Great. So I'm currently a postdoc at the Institute of Earth Sciences at the University of Iceland, but today I'm presenting my PhD work, which, as Akim said, was at UT Austin on Holocene jökulhlaups in southwestern Iceland. Most people here probably know what a jökulhlaup is, but for those who don't, it's an Icelandic term for a glacier leap. In many parts of the world, it's called a glacial lake outburst flood or gloff. And effectively, these are sudden rapid drainages of glacial meltwater. And glacial lakes can form in a lot of different contexts, dammed by bedrock, ice, landslide, or moraines. They can be in front of glaciers, underneath, on top of, on the sides. And there are several processes that can trigger these outburst floods. One is subglacial geothermal activity or volcanic eruptions, such as we see in Iceland. But in most parts of the world, it's more from dam failure of glacial lakes, or the lake level simply fills and spills, it exceeds the dam height and then drains, or there's a mass movement event like an avalanche, a rockfall, a landslide, or a glacier calving event into the lake, which then generates an overtopping wave that drains in a flood. There are a lot of different directions jökulhlaup research can take. It can tell us a lot about how glaciers and ice sheets have responded to past climate changes. They have a very big role in landscape evolution in terms of high magnitude, low frequency events and rates of geomorphic change. Perhaps obviously, they can tell us a lot about glacial and proglacial hydrologic systems. And finally, geohazards. These floods can pose a significant threat to downstream communities and infrastructure. And jökulhlaups leave a very distinct geomorphic signature on the landscape. Here's a schematic diagram showing an idealized, with idealized stream power on the y-axis and flood time on the x-axis. And as stream power increases over a classic hydrograph, different geomorphic thresholds will be crossed and generate features. So first sediment is eroded, then bedrock, like sort of smaller scale grooves or flutes or scours. And when stream power exceeds another threshold, basalt will actually be plucked and produce steps, or in extreme cases, entire basalt columns, and excavate canyons very effectively. And then as flood stream power drops, material falls out of suspension as competence drops. So first boulders are deposited, and then smaller particles like gravels, cobbles, and sand and silt. And mapping and interpreting this evidence is very difficult in many cases. Sometimes it's obvious, like here in the study site, classic glacially striated bedrock. Here's some classic jökulhlaup erosional evidence, but much of the landscape will look like this, which is very ambiguous with no clear geomorphic signatures. And there are lots of challenges that come along with this geomorphologic interpretation: equifinality, feature preservation. Floods often drain multiple times along the same route, and so linking a landform to the specific flood event that formed it can be very difficult. We usually don't know pre-flood topography, at least not exactly. And finally, whether the absence of a certain line of evidence is in fact because that evidence never existed, or because it's simply not been preserved in the landscape. So all of this gives a short, almost theoretical framework for my study, which is in southwestern Iceland. And to understand this, we need to go back to the late Pleistocene, when Iceland was covered by the Icelandic ice sheet, which reached up to nearly 2 kilometers thick in the center and out to this red and black line, well past the modern day extent. And as Earth warmed the Holocene, this ice sheet began a rapid retreat. By about 14,000 years before present, it was in the dark gray area. It advanced again during the Younger Dryas, and then retreated briefly and advanced during the Preboreal. But between about 11,200 years ago, when ice extent was at this black outline, and about 9,000 years ago, when ice was at more or less its modern extent, as shown by these dotted areas, this timing and pattern of the final phase of ice sheet retreat is quite poorly constrained in Iceland. And as you can see from the black line to the dotted line, that's a huge amount of ice loss in a relatively short amount of time. And there's some evidence throughout Iceland for glacial lakes that formed to store a lot of this meltwater, and one is Glacial Lake Kjörler in the South Central Highlands. And one publication by Thomason in 1983 has mapped some of the flood evidence from these jökulhlaups that presumably drained from Glacial Lake Kjörler. But until I came along, that's the only study that's really focused on the geomorphology of these events. So my research generally aimed to better constrain flood timing and dynamics. So I wanted to know where these floods drained and how they impacted the landscape, when they occurred and what was recurrence interval, and what was peak flood discharge. And the idea was that this could help us better constrain the timing and pattern of this final phase of Icelandic ice sheet deglaciation, and also potentially be an analog for modern day climate ice hydrology links, as well as those from other ice sheets in the past, and the jökulhlaup cycle, where ice dammed lakes will repeatedly fill and drain. So again, we're in southwestern Iceland, off the southeastern corner of Langjökull, which is Iceland's second largest ice cap. And much of this work was based on geomorphologic mapping. So I spent about 4 summers up here hiking around the landscape and mapping features. And a lot of the landscape was pretty ambiguous. Some of it had clear glacial landforms like till, bedrock striations, glaciofluvial sediments, and some striations marked in with these black arrows. And there was also quite a bit of definitive flood evidence. And I've shown it here in blue for the erosional features, with darker blue marking more pronounced features like canyons, and then more almost lightly scoured bedrock as a lighter color. And then also depositional features, which are in red to pink, again, with the darker colors representing larger scale features like boulders, and then light pink as gravel bars. So this gray area is the entire area that I field mapped, and it's about 30 kilometers total from this mountain Blaufell to Gullfoss waterfall, which is one of Iceland's most famous and was the southern end of the study site. Rather than go through extensively, I've got to just pick a few highlights for features here. And a lot of these occurred multiple times throughout the study site, but this gives a sense of these smaller scale sub-meter scours progressing to more bedrock steps, and then finally cataracts, which are amphitheater shaped erosional features. This one has a plunge pool where the force of cascading water created a depression. And then presumably a lot of this excavated material was deposited on flood waning stage. And you can see from this photo in 5.4, you can actually still see the columnar structure of a lot of these rocks that have been deposited, suggesting little modification. And then we also get a couple of large-scale canyon features. These ones are called Korkiel, and this is a really nice cataract with a flood-eroded notch. It's about 50 meters deep, which would have been excavated by Nick Point Retreat, rapid erosion of rock. And in each of these, the blue arrow shows hypothesized flow direction. Here's another example. These are also flood channels, but on a smaller scale than the previous ones. But you can still see some flood eroded grooves and flutes, though a bit more broken up. And finally, we enter a wider topographic area, so more unconfined flow. And so you'd expect more deposition, which we do see. Here's about 1 square kilometer field of boulders, and these are up to 2 to 3 meters diameter. So it gives a sense of the scale of some of these features. And then finally, we get to the downstream most part of the study area, where we have the Kvitárgljufur Canyon, which is about 3 kilometers long, about 200 meters wide in places, and over 50 meters deep. And this is a really nice box-shaped canyon that's quite typical of flood-eroded landscapes and basalt terrain. And this is a potential trough. You can see the basalt columns. So these would have likely been fractured and then plucked by very high stream power, and then excavated downstream to leave this box-shaped canyon. And here's another example of what you can do with this geomorphologic evidence, since field mapping doesn't give you the perspective you need sometimes, and aerial photographs didn't quite have a high enough resolution. We drone mapped the canyon, and this gave us higher resolution digital elevation model and imagery. So we were able to map some other eroded troughs, this blue outline showing the boulder bar, and also potential different Strath Terrace elevations. And here are a few examples of showing this sort of slot canyon where the modern day river has eroded, but then you can see these paired and unpaired Strath Terraces, which are clearly more flood formed. They're wider, they're more box shaped. So to interpret all of these different features can be quite challenging, but using geomorphologic interpretation, different landform assemblages, the topographic context, I've identified 4 potentially unique flood drainage routes. And the flood inundation area that we've mapped differs a bit from that mapped by the previous study by Thomason. His is in green, so you can see a few areas where he mapped flood evidence, but we didn't find anything definitive. And then also some areas where we found evidence, but it had not previously been mapped, notably this third flood drainage route. And some of the flood margins are field surveyed and have clearly constrained glacial margins. So for example, there's glacially striated bedrock, but no flood features after this dark or this black solid line. And then some areas like the black dotted lines are field surveyed, but have very ambiguous evidence. So it's not a clear flood margin. And finally, the red shows areas where we have not yet field surveyed. So the flood inundation margin is poorly constrained there. Additionally, we looked at flood hydrology to try to reconstruct how big these events were. And there had been a few initial estimates, but I also used boulder paleocompetence to add in. So here you identify some of the largest boulders at different sites, and you measure the dimensions, the roundness, and parameters like channel slope and cross-sectional area. And you can use all of these to estimate the flow power required to transport these clasts. There's a second method to reconstruct flow hydrology, which is with Manning's N equation. And this looks at flood channels and uses cross-sectional area, slope, a few other parameters to estimate how much water would have flowed through this channel at one time. So you can see here that this one is about 100 meters wide, just over 50 meters deep. And then you can calculate a peak flow discharge based on this cross-section. These yielded first order approximations of magnitudes on the order of 10 to the second to 10 to the fifth cubic meters per second, which roughly agrees with Thomason's previous estimates. The highest I calculated was around 300,000 cubic meters per second, which would make these among the largest known floods in Iceland. But there are a lot of caveats with both of these methods, especially channel cross-sectional areas in Manning's N. For example, you're assuming that the entire channel was full to the brim with water, which it probably wasn't. These could have been eroded in multiple flood events or progressive incision during the course of a flood. You're using modern day topography, not topography at the time of the flood, but at least it gives us some estimates to work with. And finally, to determine when floods occurred, we're using chlorine-36 cosmogenic nuclide exposure dating. And the idea here is to get a couple of control surfaces, like here is in between flood channels. So we would expect this one to be more of a sort of control on the time of deglaciation. And then to get some samples from within flood channels where this would likely record the time of the flood or when this overlying rock was eroded and exposed a fresh surface for this geochronological clock to reset. And to get a sense of what some of these surfaces look like, here you can see there's still some flood scouring, so it hasn't been modified much. It's an encouraging surface to date, and you basically chip off the top 2 to 3 centimeters of rock and send this to the lab for exposure dating. Unfortunately, there were still some delays, COVID-related lab closure delays, so we are still waiting for dates, but we're getting really close this time. So what does all of this mean for the Icelandic ice sheet to reconstruct the behavior of the final phase of this deglaciation? These are hypothesized scenarios. A lot more needs to be done to pin them down. But in one scenario, you've got a more southern ice margin that releases floods along one set of channels here. The ice margin then retreats. Another set of floods drains and forms these anastomosine channels, and then continues along this topographic valley south to Gullfoss, but leaves these ones abandoned. And then we've got another set of channels that seem to have a different orientation and don't seem to be continuous with this second set, and that would imply a potentially different source. And finally, some floods around the eastern side, which still needs to be ground truthed, but this is a lower lake outlet elevation, so it would make sense that the lake would have drained after the ice margin had retreated from farther to the west. So in conclusion, there's extensive jökulhlaup geomorphologic evidence across this landscape, showing a very complex drainage pattern with 4 distinct routes and 2 potential sources. There's no definitive evidence for multiple floods along each route, which could be an issue of preservation since ice-dammed lakes typically drain repeatedly, and we see multiple shorelines in the lake basin. First order approximations at peak discharge span 3 orders of magnitude, but at least are initial estimates, and chronology is to be determined. And for the next steps, there's a lot more geomorphologic mapping that can be done. Also constraining the shoreline elevations and lake volumes in the actual lake basin. I don't know how well you can see these shorelines, but they're there. And finally, this can also be used to calibrate and pin ice sheet modeling. So those are my next steps. Your next step, if you're interested, is to read the paper that came out last week in the Icelandic journal Jökull that has a lot more information on this. So thanks very much, and I hope you have some questions.
Okay, so very much for inviting me, and there have been very interesting presentations so far, and it's nice to be able to tell you about our work in this subarctic mountain environment in Northern Norway, where this background picture is from. Yes, I've been involved with circumpolar permafrost studies quite a lot last years, but this like more local scale geomorphological studies are close to my heart, and I'm very happy to tell about them and to work with them a little bit more nowadays. So here are the aims of our work in this area and also this presentation. So in this area, we have mapped periglacial landforms and their activity across quite a wide environmental gradient. By this, I mean that the elevational range of this area is from the 100-meter near the major river valley here, and yeah, it's about 100 meters above sea level, and the mountain tops are well above 1,000 meters. So there's quite a nice vegetational and climatological gradient. We can see here that the modeled mean annual temperatures are close to 0 here at the corner of the study area, and close to -6 Celsius in the mountain tops, fell tops. Yes, first we have compiled field data, then we compiled geospatial data from GIS and remote sensing data in order to perform some predictive spatial modeling in this area. And also we have used radar satellites, more precisely this interferometric synthetic aperture radar data, which we can use to measure the ground displacements in this area and relate them to the mapped periglacial activity to see if they coincidence. Little bit about our study area. So it's located at the 70th latitude. Northern Norway is just across the Norwegian-Finnish border, and it includes those 2 major fells, Rastikaisa and Geatnukaisa. And there's something about the geology of the area. So it's Precambrian crystalline rocks and shales, and extensively covered by glacial till and very extensive boulder fields on the higher elevations, and also some glacial fluvial sediments across the area. One interesting aspect of this area is that it's one of the largest remaining relatively untouched wilderness areas in whole Europe, where this our study area is situated. And from this Nordic permafrost map, we can see that the area has sporadic and discontinuous permafrost. So the permafrost extent hasn't been studied in this area, but most likely the mountain tops have permafrost quite extensively, and then some patches when we come to lower elevations, and no permafrost when we go back to the mountain perch forests in the lower elevations. Here's a view from the top of the Rastikaisa mountain towards north. This shows the large wilderness area that still remains quite wild in that part of Norway, and we can see that this is a photo from beginning of July, and there's lots of snow still, and some of it doesn't melt during the summer, so there are perennial snow patches such as the one in the foreground here. So usually doesn't melt during the summers, and these are one of my main interests in this area. This the recording went out for a minute. I hope you still can hear me.
Yes, it was something. Don't care about it. Please just go
Okay.
on. Continue.
Yeah. Very good. Yeah. For comparison, this is a photo towards southeast, towards Finland. The same day, we can see that lot less snow and more gently undulating fell landscape, not like so mountainous as it is in Norwegian side, and also in Finland side here in the horizon. It's also a large wilderness area, and but here permafrost is confined to balsamires mostly. Something about Pearce has a base map of the area. Rastikaisa and Jäätnökaisa fells are situated like this, and during summers 15 and 16 we visited about 700 sites, then by 10 meters each, which are here marked with dots, to map some periglacial features that happen to occur in those sites and to estimate how active those processes were. And there's this small inset photo that shows some fresh frost action, which is one of the ways that we assessed how active is the frost-related processes in the site. Also, we measured some topographical and soil property characteristics at these sites to be used in models, and some photos about periglacial landforms processes. So we included cryoturbation features such as pattern ground. One form is showed in this picture here, and earthhunks and so on, and then also those slope processes, fluctuation processes, including lobes, terraces, and ploughing powders, such as the photo here. It shows this rock that is moving faster than the surrounding soil material, and it pushes some dirt material in front of it, and it's a very active site of solifluction. And also nivation or processes related to snow accumulation. Both erosional and depositional processes occur at these snow accumulation hollows, and these hollows can enlarge as snow accumulates and these processes work. Some results from these mappings. So we found that in this area, periglacial activity starts to occur basically right after the tree line. So as soon as we are out of the mountain birch forests, which in these background maps, which so vegetation amount, these per mountain birch forests quite nicely correlate with the screen colors, the lower corner here, and everywhere above that line we had some sort of activity recorded in suitable conditions, although the highest activity was found at fell slopes and mountain tops. For example, here solid fluctuation map shows that the mountain summit areas and slopes had the highest activities. And here's greater patient. There are some flat areas here and there where suitable conditions for pattern ground occurred, for example, and innovation was occurring basically anywhere where the topographical conditions were suitable. And then how to model these processes? Well, we are use statistical modeling approaches which need input data from GIS or remote sensing data. And in this case, we used digital elevation models and optical satellite imagery of different pixel sizes to derive this kind of environmental variables on surface geology, topography. For example, here we have a topographic wetness index, for example, and also about the snow cover duration in days. The map A displays that one, and vegetation conditions for optical remote sensing data, and also we modeled some mean annual air temperature for the area. And with this we try to explain what kind of factors affect the activity that we mapped at the field. But in addition, we used this INSAR radar satellite data to measure these ground displacements or the velocities across the area. They are basically, INSAR method from Sentinel-1 satellite can acquire millimeter scale measurements, ground velocities, and we average them over the snow-free seasons from a couple of years, and found that this map shows horizontal velocity, and so lateral movement, and then also vertical velocity, and we found it where the most rapid movement occurs in this area, most places, slope areas and summit areas of these two fells. However, the movements were not too fast, usually less than centimeter a year on average. Yeah, this INSAR data is really interesting. It provides opportunities to assess this kind of movements across a very extensive areas. And it has also been used frequently studying land deformation or, for example, surface subsidence due to permafrost thaw in many regions across the Arctic and the Tibetan Plateau, for example. And then, yes, those were the data that we used as an input for statistical modeling. And we published one article where we, instead of using field measurements of periglacial activity, we used these INSAR-derived ground displacement velocities and tried to predict their distribution using statistical modeling, regression, and machine learning-based methods that took into account the possibility that the relationships are not linear but non-linear, and change as the values of the environmental variables increase. And I won't go into detail with this approach here, but this is the diagram that illustrates different kind of sampling methods that we use to take some samples of these INSAR observations and then fit statistical modeling and explain the variability of ground displacements. And we found from INSAR data that spatial distributions of horizontal and vertical velocities were different. and that vertical velocities could be more reliably explained. There are two values for 0.47 for the model calibration, so we could explain 47% of the variability of these velocities, and it's however decreased to 28% when we predicted to evaluation data sets that were extracted from the INSAR data. And also this is one photo from our article that shows that the highest velocities quite nicely coincident with the high solifluction activity rates that we had measured, although this figure doesn't show the actual study sites, but just aerial photography of the area depicting different kind of slope processes, and we can see that solifluction quite commonly occurs where high velocities were measured. It's not a perfect match at all. There can be some mismatches between the spatial resolution of INSAR data and the scale of those processes happening. So there's room for improvements. We also asked what factors actually bring about these ground displacement, or these how fast they are, and found that vertical velocity was mostly influenced by air temperature and vegetation, while horizontal velocity was most strongly related to slope angle. The higher the slope angle, the faster the movement in the horizontal direction, until certain point to reach this so-called response curves flattens. So we didn't have slopes higher than that, or the solifluction processes, for example, didn't occur at slope angles higher than that. Some discussion or conclusions about these results. So first, we found that periglacial activity is quite widespread in the study area, which is quite understandable because it's quite a cold area, clearly below zero in annual temperatures. And we also found that integrating statistical modeling and those INSAR provided ground displacements could lead to insights into environmental factors that affect periglacial landform activity. And that could be done in extensive areas. Yeah, like I mentioned, the models were not perfect. There might have been a scale mismatch that we couldn't use the INSAR data to recognize fine scale processes that occur in this area. For that reason, it was that performance of the models was lowered. And finer resolution could help that, and also we could give more weight to some important environmental conditions such as soil properties, which of course are very central to these periglacial processes. Some future work that is we are doing right now or in the future. So using this field data, we can perform quite detailed assessments of the fine scale controls of these activity rates that we mapped. And using INSAR data, we can extrapolate models to quite extensive areas, and so that offers new opportunities. And also climate change is one thing to consider to see how these processes may react to changing climate. Thank you very much. Here are some references related to these studies. Of course, I haven't done this work alone, but there are many teams from Finland and from Norway, for example, I should mention these INSAR data were processed in Tromsø, in Norse Institute by Line Ruet, mostly. So that's one thing that I need to stress. So thank you very much.
Thank you.
Hi, good afternoon, everyone. Thank you for the introduction. Yes, and I will be talking about scratching beneath the surface. So combining geomorphology with geophysics, essentially. A bit of my background. I did a bit of a ping pong between industry and academia, where I started acquiring geophysical data offshore, came back to do my PhD, went offshore, went again into the industry, and I worked with geomorphological and geophysical data, as well as geological data to build ground models for wind farm developments recently. And I'm back in the academia at the moment, so it will be a talk in two parts, and I hope to bring it back home at the very end. So bear with me, please. First of all, as I mentioned, talk in two parts, and there are two study areas that I'll be talking about. So I'll be talking about geomorphology of ice contact deltas in Finland, and using near surface geophysics, what this can tell us on top of the geomorphological assessment. And then I'll move to the southern part of the Baltic, where the same ice sheet was retreating a bit earlier, but that landscape is now submerged. So we cannot see it directly. And in fact, most of the landforms there were maybe not obliterated, but altered by marine processes and lacustrine processes, and the primary glacial small-scale features may not be that well preserved, and I'll talk about it later. So, and that's where you use different kind of geophysics there. So first of all, study site here, Selkas near Lahti is where I went during my PhD to acquire some of the data to look at the beautifully developed systems of a very long moraine, that actually two or three of them, depends where you are, that span across the southern part of Finland. And they are absolutely gorgeous. They are also linked to an ice margin sitting in the Baltic Ice Lake at that time. And they were dated pretty well. They are dated to be developed very quickly. One of them developed around 200 years, give or take, and another one potentially 250 years, possibly even shorter. And they're not small as well. The deposition occurred rapidly. This is how they look in LiDAR data, and this is probably the best way to appreciate them, because in fact, that region, that area is quite heavily forested. So that landscape appreciation that we got from some of the places that we had presentations from before, where the landscape is barren in terms of vegetation, that appreciation there is slightly gone. We just don't see that scale of the features, yet they are great, huge, and very complex, as you can see this one. We did a lot of geomorphological mapping. You can see multiple ice marginal positions, retreating and re-advancing ice margins, braided river systems or braided stream systems on top of deltas, or on the delta top sets. Very steep slopes towards the south, where the Baltic Ice Lake was sitting at that time. Multiple cattle hole lakes, the Giro moraine south and north of the deltas as well. There's just a lot of that going on, and it's clear that it's not just an ice margin and a very linear ice margin sitting idle and depositing and then stepping back. So that got me thinking, or that got us thinking, that there's more hidden underneath, and how can we decipher or reenact that history of deposition in this place. And this is another delta ridge. This is just 20 odd kilometers north of the previous position, and there are deltas that are probably slightly less complex, but maybe with slightly better access. So instead of doing that in the city center in Lahti and on a very large, geomorphic feature, we focused on a smaller one that we can actually comprehend properly. So we did the same. There's as well as in the previous one, you can see that there are multiple ice marginal positions. Some of them potentially disappear under that delta. There are also features like eskers coming in and disappearing underneath the deltas. So there's once again a lot going on. So geomorphology tells us, without even looking further, is that we can have a distribution of the delta sizes, so length versus width of the deltas, and there is a trend. So we can see a trend where the deltas are lobate, so the circumference of the delta with respect to the width, and some of them are really bench-like, so they're quite flat or not, they didn't prograde that much. And at some point around here, we seem to be losing the lobate deltas around 5, 6, 7 kilometers wide deltas are lobate, and beyond that they're mostly are quite bench-like. And we attributed that to essentially deltas amalgamating together. So in fact, you have two deltas building as lobate deltas, and at some point they just meet laterally. And in fact, what happens is they just then exist as a single system, possibly buttressing the sediments of each other a bit, but that also constrains slightly the drainage system or the or meltwater outlets in the ice margin, how wide they were between each other. But this is as far as we can go. There's obviously a bit more in terms of the history of kettle holes and how the ice was stagnating and developing there and collapsing. But there are also some small bedrock controlled deltas which are relatively short, but they are not lobate at all. They have a flat frontal part, let's say. So essentially they prograde in a confined environment. So we call them bedrock controlled. But then we can do a geophysical evaluation of that to see what the history and what story is hidden underneath. And this is what the data looks like. So the pink lines are the gravity lines that were pre-existing, acquired by GTK. They're really helpful. And we did GPR, and which is ground penetrating radar study, and electrical resistivity tomography lines, which are in blue here. Now GPR is relatively easy to do. Oh, and we studied sediments as well. GPR is relatively easy to do. As you can see, some people find it hard work, some people don't really. And ERT, ERT is time consuming. You need to put every spike in the ground and roll over, and it takes days to acquire lines over a couple of kilometers. So I think it took us 8 days to acquire 2 lines. But the results were very helpful, because now we can see what the delta structure looks inside. And this is a cross section of a very simple delta. We certainly targeted that delta because we knew what we would find inside, and we wanted to have a benchmark, really, a confirmation of what we can see. And we can see clearly the faucets of a delta prograding that seem to change in angle. If you look here, there are smaller bed forms prograding in here, higher amplitude ones, and finally there's something around there which we interpreted as a bedrock high, and there are bigger faucets, Gilbert type faucets, prograding into the basin. And change in amplitude across we attributed to the change in terms of the position environment, proximal to distal of an ice contact delta. This will be the ice contact fan, where there will be a direct influence of ice push and possibly coastal fascies. The position, there will be a part where there is an overriding ice depositing probably traction tails on top. And this is actually interpreted as very well sorted or moderately to well sorted faucets of sands and gravels steeply deeping into the basin. But then what we also discovered quite quickly is that GPR is not giving us enough penetration. In places we can see things well, in places we know from gravity, which is here in gray, that we don't even sample the half of it. The rest is just a mystery. We know there's a borehole here touching bedrock there, and that part is not imaged at all. We don't know what's going on. And there are places where stratigraphy gets really complex, like here. You can see this is probably some kettle holes. This is not artificial. So they're all dead ice blocks sitting in here, and the delta was depositing sediments around them somehow. So they were grounded in that Baltic ice lake, very close to that delta. There are also beds which seem to be coinciding in some clay layers in core, which means that there probably was some period of non-deposition and settling from suspension, sediments sitting on top of that delta, and then another rejuvenation of deposition in that region. Very complex story. So the ERT lines help to decipher that a bit. So we can actually start seeing the internal structure slightly deeper, albeit with less detail. And if we overlap the GPR interpretation across one delta here with ERT, we start seeing the zones where the resistivity of the sediments, of the sediment pile, starts to correspond with electrical response of the ground. And we immediately see that there are zones like here and there, where there's this moderate or intermediate resistivity value, as opposed to this part where the resistivity is low, and we assume this is linked to aquifer and clean sands, whereas this is probably more mixed material here and there. So that's immediately starting to build a story for us, and we combined all the geophysical methods and models into this. So each method alone will give us a slightly different answer, but there are limitations to each method that we needed to be aware of. So, for example, GPR, if we were to just interpret based on GPR, assuming that the end of the signal was the end of sediments and identification and the position of bedrock, then we would have ended up with this model, which certainly wasn't true because we had boreholes penetrating deeper. Then ERT showed us this kind of model where we started looking at two different fascies depositing in a proximal to distal zone. And then finally, the gravity chipped in, and we knew that ERT in the very conductive part seemed not to peak at the base, and it looks like it's actually the electric, the current is sliding on top of a very on the aquifer. It seems like the aquifer is such a high contrast in resistivity that we're picking the top of it rather than the base of it. So if we were to combine the three together, we ended up on this model where there are hidden overdeepenings filled with sediments and filled with water. And above that water table, we see the delta, which is highly complex with prograding fascies into the basin, but that part, the proximal part, is composed or compiled of very variable, very different mixed proximal fan and ice push, ice bulldozing type debris flows and deposition. But some of that correlates quite well with other features that we see in geomorphology. So we started thinking about scenarios of how this delta developed. The top side, the top sets of the delta are actually blanketing some of the older geomorphic features. So we came up with two scenarios. So one of the scenarios is that we had an ice margin sitting here and just depositing a small fan. The other scenario is that there was a pre-existing esker, a complex esker deposited here, and the ice margin was just on a part on the other side of it. And then finally, the ice steps back in both cases. And where there is no esker, we just have a progradation, and the progradation of the delta blankets the ice marginal position, which we can potentially see here. And there is just a ridge in the middle of it. And that ridge eventually gets buried, and that's how the delta developed on top. The other option is that there is an actual esker that also gets buried. Why is this important? For this particular place, and in Finland, those deltas are local aquifers. They are actually perch aquifers atop of impermeable bedrock. And the connectivity of water laterally or distally to proximally of that delta is important. So if we were to introduce a lateral or east-west barrier to flow, we would compartmentalize the aquifer in a different direction than if we were to introduce an esker going north to south. That's a very applied implication of that. And I thought that was very interesting. We came up with those two scenarios and ways to test them. And this wouldn't have been possible without geophysics in it. And that brings me to the other part of the story, because now we're moving into another ice marginal position, the same ice sheet, and now it's a submerged landscape. And this landscape is interesting because, well, some part of it, especially here, was submerged for most of the time, but where we are looking, which is there, this was the water level. Or this is the seabed level currently, and obviously it was submerged by the Baltic Ice Lake and then Ancillus Lake again. So a lot of the landforms that we can see in places like Salpausselkä around Lahti, Finland, are gone because of the longshore drift currents. Geomorphic expression of mobile bed forms is overtaking any post-glacial or glacial geomorphology in the region. But we know that this was a nice marginal position that was pretty much well dated from core, and the ice stagnated, retreating from Poland northwards around 15.6 plus minus 0.6 Ka at that location. Because of the scale of this place and because of the lessons learned from Finland, we know it wasn't just a simple stagnation and simple deposition and then step back again and deposition again. We knew that this sediment pile is very complex, likely more complex than anyone can imagine. And internally, it will take a lot to understand what's going on. And this is also important because this site is a very prominent site for wind farm development now. All the blue polygons are licensed wind farms. They will be built in the next 5 to 10 years. All hashed polygons are actually proposed wind farm sites that are still undergoing licensing rounds. So they may be built, but not necessarily. You can clearly see that they are all built in the ice marginal setting because it's very convenient to have a shallower ground further offshore. You can hide your wind farms easier. Understanding that is crucial to the approach you take to ground modeling, because if it's a complex ground condition that you're dealing with, you need to schedule your surveys better. You need to understand what is the minimum or the key uncertainty or key limiting factor in terms of geology and what kind of geology or in geomorphology you can expect there. And finally, there is one more thing here, the history of the inundation or sea level change here. This particular part of land of the ground was actually well, an elevated area which was partially submerged and was damming an ice damped, smaller ice damped lake, a proto-Baltic ice lake, if you like, on the higher ground. And then the ice margin stepped back and the first proper Baltic ice lake stage started, and then slowly, ever so slowly, that area is submerged again. So the position happened between ice marginal marine and ice marginal lacustrine to ice marginal terrestrial setting. So this is one of the diagrams I made a few years back for one of the publications, and those are the potential landforms and sediments to expect in each setting, in terrestrial setting and in large periglacial lacustrine. There are several differences, significant differences of what can be expected, and this is important to understand and start screening for what we can see in the subsurface and on the surface. There are also the options that are small kettle hole lakes present there. So within the terrestrial part, it's not unlikely that you will have kettle hole lakes there. So that's how this will look like evolutionary. So you'll have from the in between the terrestrial to grounded marine ice sheet margin depositing variety of sediments and landforms there. So what do we do to actually start seeing that? We take a boat and start acquiring seismic data. Different sources, single channel, multi-channel, I'm not going to get into detail. We tend to sail them on a grid because this is a 2D data in this case, but we're getting towards 3D now. So 2D data provides us cross-sections and geophysical cross-sections for the ground, which look like this. Then we can apply and interpret that and apply some principle of seismic stratigraphy and seismic geomorphology to actually see some features in the plan view, essentially landscape evolution in the past in time slices going upwards towards the surface. And it's really, this is where it gets exciting for me, because before that was the domain of big oil and gas companies paying big money to actually do it in deep offshore settings to find oil. Now that zone that close to the seabed, the first 100, 200 meters was always neglected. But because of the rise of wind farms and wind farm industry at the moment, what we're looking at is a rapid growth in techniques and tools and data availability for the first 100, 200 meters, where the resolution now gets to 0.5 meter. So we are looking essentially at DEM quality subsurface information, if we can get it. This is where it gets really exciting for me. So for example, this is how the data looks like in a cross section. and this is how you can interpret it. And that interpretation here gave us two essential glaciogenic units. Before that, there's bedrock. Above that, there are post-glacial sediments. So I'll go quickly through glaciogenic unit B, which looks like that in the cross-section. However, if you start mapping that, this is what you get. You have very long, undulating, wide channels, and the bottom of the channels is actually going up and down. This is likely a telltale sign of tunnel valleys buried under a pile of sediment. This is probably the first time anyone actually saw tunnel valleys in the Baltic Sea, although we know they exist on land. Now, then we have other piles of sediment that are above it. There's a prominent erosional surface subdividing the two units. And that sediment surface is here, and we can see a pile of sediment with this prominent ridge. That is an ice margin. Basically depositing the pile of sediment, pushing it over and modifying it glaciotectonically. You have folding, and a lot of complexity in this ice marginal zone. So that's the first ice margin. But then, see, you can see smaller details. You can see smaller channels developing in front in the hinge lines of the small glaciotectonic folds. You have trusts, and this is not to scale, but this is how the ice margin would have looked like. And then we have a second ice margin, potentially there, backfilling this small basin here with ice proximal fan fascies likely, which can be described as this situation. And then finally, there's potentially a third ice marginal position that sat somewhere here that in a way prevented this sediment pile from going anywhere and provided a small mini basin between the ice margin and the former ice margin position to be backfilled again. This data, however, doesn't give us an indication of what is the variability of sediments. But when we go back to Finland, this is how the sediments look like in Finland. You can see that car, and this on a scale of potentially 50 to 80 meters, we have a very different sedimentary package present, from very fine sand and silts to very coarse cobbles and gravels. And this is the heterogeneity within the system that we need to deal with and need to communicate to someone who wants to build a wind farm. And finally, then we can also take a stock of our surfaces and extract some of the seismic attributes, meaning amplitudes in this case, and we can actually start seeing the geomorphology of the features and things in the subsurface. So these patches here are actually the fill of the lakes. The lakes are filling the small topographic lows, but they are connected, interconnected, very patchy. So this is probably the first time that this can be actually seen properly. You can map this out, and we can understand the properties of the ground thanks to the geomorphological, seismic geomorphological approach. Now, then we have those undulating tunnel valleys, which if we map out, we can see where the water was flowing, leaving the bedrock highs around, eroding around them, and rooting down towards the south. And that's how it looks in thickness of sediments, and elsewhere they are present across the site as well. So lessons learned. This is just a representation. We don't have any understanding of the sediments inside or the fascies within it, and we won't have, because we have no way of accessing that data. However, if we look at different ice margins elsewhere, we know that the complexity is great. If we map that, we know the action of ice affected that region massively, and the pile of sediment will unlikely to be predictable on a short scales even, like in here. And finally, we can use that knowledge to apply that to our ground models, to apply to our geomorphological and geological description of ground models, to communicate the uncertainty with that to the people who will actually will be building those wind farms. And I'll finish with that. So lessons from onshore geomorphological and geophysical investigation can be almost directly applied to similar settings offshore, but we need to have a good understanding of our depositional settings and our geomorphology and landscape evolution. And in many cases, the geophysics and seismic geomorphological approach can shed new light and let us understand a few things better And it's very powerful. It's just becoming more powerful and more appreciated in the industry and elsewhere. To date, however, this was hard for seismic geomorphology in glaciogenic settings because of the resolution of the data, but that's changing rapidly, and this is exciting. These times are getting exciting ahead because we are getting towards 2D high resolution and towards 3D. So we can potentially start seeing a lot of very accurate post-LGM and very recent glacial or pre-glacial or post-glacial landscape evolution models thanks to that data set. And that is a powerful tool both for the industry, but also for our understanding of how the Earth works really in the very recent past and how the climate has changed since. So there are some papers that this work was based on, but that figure on the right-hand side came from this line paper from Benjamin, who did a great job in the Barents Sea, looking at state-of-art data, and that surface is not bathymetry, that surface is actually buried, and you can see the bathymetry-like quality of what features and landforms can be seen there. And with that, I'd like to finish, and thank you very much for attention.